Thank you again for accepting the invitation. It is our pleasure to have you here with us in our CSIM series of seminars. So I would like to introduce Dr. Aiman, who is the head of the Information and Computing Technology Division at Hamad bin Khalifa University. Dr. Aiman, previously he holds several managerial positions at Qatar University. Okay, director of research planning, director of research. Okay, and he was also the coordinator of the computer engineering program. He obtained computer science from the University of British Columbia in Canada, the master's from the University of Essex in UK, and the BS in computer engineering from the University of Washington. He is very active in the IEEE community, receiving several awards, at conferences and at known journals. And he is a senior member at IEEE and ACM. The title for today, as you can see, is Distributed Inference in Resource-Constrained IoT Edge Computing Devices, Challenges and Opportunities. Well, so with no more words, thank you again, Dr. Aiman, for accepting the invitation, and the floor is yours.
Thank you so much, Dr. Nizar, and thanks to the great audience, Dr. Mohsen, Dr. Devram, and all our colleagues here. So today I want to really talk to you about a very interesting topic, which is distributed inference and resource-constrained IoT edge devices. We'll talk about very specific 2 case studies, but through these 2 case studies and through introducing this topic, we would like to explore some of the challenges and opportunities for interesting work in this area. So I'll start by motivating the general area of pervasive AI before we focus then on the distributed inference part. And the 2 case study, one will be in a multi-drone mobile environment, and one will be in an IoT environment. Both are surveillance application. And then we will get into the future work and conclusions. So if we are talking about IoT, we are talking about an area that is really growing exponentially. As you see, this was coined, the term IoT was coined in 1999 by Kevin Ashton from MIT. And the market size of the IoT is expecting to grow over 1.5 trillion by 2025. We are expected to have more than 5 billion devices. We are expecting to have more than 70 zettabytes of data generated. So this is a place where growth is expected fast and exponentially. And AI, as you all know, is being adopted, whether it's machine or deep learning, natural language processing, vision, which is the application that we will use today for both our case studies. And it's also an area that is growing exponentially in terms of adoption. And as we move into new architectures of these IoT systems, edge and fog computing, we are moving away from the central cloud architecture into these new architecture where decisions are made at a faster pace. And you can also see that the adoption is high. If we start looking at the generic architecture where everything used to happen in the cloud, where the IoT devices will send all of the data that is captured from the IoT device through the network fabric all the way to the backend, we'll see that there's a lot of scalability issue. The cloud becomes the bottleneck. The data is immense and huge, making it very hard to store efficiently. When we send all the data, the bandwidth will be also be used quickly by all of these devices that are connected to the internet, assuming that they will also upload all the data. These devices are battery limited, so the energy is very important, and sending things over the wide area requires a lot of energy. So this is also a challenge. The privacy of the data is also becomes problematic as we send all the data to the cloud. It goes through the whole networking fabric, reaching the cloud, and is also susceptible to cybersecurity attacks and exposures. And we have seen a lot of those in the recent past. So what we are moving toward now is this idea of edge computing, where instead of sending everything all the way to the cloud, now there is this middle layer, the edge, which resides closer to the end user by the tower or maybe in a location to cover a specific location. And now a lot of the communication happens with these edge units, and then these edge units send part of the data to the cloud for archiving purposes and for decision making and synchronization purposes. So the issues of scalability, storage, bandwidth, energy, and privacy is reduced now because we are not sending all the data to the cloud. The data is more localized at the edge, and hopefully the edge will include entities that have some trust domain shared across them. And the energy will be only the energy to communicate this data in the short-range communication. If we look at this architecture, we'll see some deployment complexity because we have to find where to put these edges and we have to deploy them successfully. And we also have to, in a lot of times, create a new infrastructure to host these edges with some compute storage and communication resources. A lot of the telecom operators are now deploying this new infrastructure to really cover the needs of these IoT edge architecture. If we decide to also engage these edges, we have to also be aware that they cannot handle the same amount of demands as the cloud. So all of these edges are resource limited, and we have to understand that limitation and manage accordingly. And now, if we say that we are trying to engage more of these end devices, if we want these end devices now to be intelligent themselves, my camera, my mobile phone, the drone, the smartwatch, if all of these are now become more smart and all of them are now connected with 5G and maybe connected with each other through some other direct communication, then we get rid of the deployment complexity and the new infrastructure needed. So we allow these devices to share resources to build a new infrastructure on top of these end devices. But we also have to deal with the limited resources because that's even more limited as these devices are now doing other tasks in addition to contributing resource to this new infrastructure. And then we have to worry about whether we communicate more of the data to remote nodes or whether we can handle most of the computation within one node and then communicate less. So there is a big trade-off between communication and computation. So this is, in a nutshell, this area of pervasive edge computing, where we smartly distribute the distribute the computing, where we care about this trade-off between communication versus computation, where we combine this pervasive edge computing with AI, leading to this pervasive AI paradigm, making these edge devices smart, processing the data close to the edge, and doing it in a collaborative manner. So some of the things that can be done close to the device is data cleaning, pre-processing, adaptive compression. So you send only the compressed data, extracting the features from the data. So you only send the features, state prediction, and all of these things help us ensure the security and privacy and are enabled by the different network fabric that is available. So this area of pervasive AI that we introduced, we can put it in a taxonomy where there is pervasive learning. And these are the areas that we have seen a lot of work recently in federated learning, multi-agent reinforcement learning, where we do a lot of the training of these models in order to have better models and to keep the data in the devices, training on in place, or learning in a distributed fashion, in a multi-agent fashion. So you will get an optimal allocation or an optimal solution. And the area that we will talk about today is the pervasive inference. And pervasive inference is where we have these standard big models that have been proven to work well, that have already achieved excellence. And now what we want is to distribute these models across multiple devices in order to reduce the delay and manage the energy in a good way, in a collaborative way across multiple edge devices. So we wrote this new survey that is submitted to IEEE Communication Surveys and Tutorial, and it's also available in archive. So today we'll talk about these two case studies, the segment-based privacy-aware distribution and the layer-based mobility-aware distribution also in drones, one in IoT devices and one in drones. So if we start looking at the types of applications targeted, you can go all the way small to these nano robots used in healthcare applications. These nano robots can now maybe be used for delivery, drug delivery. And these nano robots are very limited in terms of power, processing, and memory. But these robots, we can have thousands and maybe millions of them to do the task that we want. We can think about smart transportation application where you have roadside units, where you have smart vehicles that need to make decisions in real time that cannot wait to communicate all the way with the cloud. But can also leverage the intelligence and the communication with nearby devices to give us the smart mobility scenario, detection of accident, traffic management, road control, and different applications that we can benefit from. We can also think of flying intelligent drones, where these drones are doing some show, like what have been done in a lot of these sports and festivals, or the drones can be doing a mission being controlled by a human operator or autonomously moving to do something smart, surveillance or rescue operation, and they cannot also wait for a long time until the decision is made. So they need to make do with the limited resources that they have. So all of these applications, including this application of a smart city, where you have different IoT devices and different entities, and what we are proposing here is that running the neural network, the deep neural network, in one device might be problematic. It might take in the order of seconds. For example, VGG can take maybe 16 seconds to run in a medium device. And these models are becoming huge. These models now have millions of neurons. VGG have 15 million neurons. It has 144 million parameters, 3.4 billion connections. So these models are huge. So if we are to run these models in this type of setup, we need to distribute these models in smart ways. So we will take the layers or even smaller segments of the neural network and run it in different devices, making sure we follow a certain order to do the service, whether it's surveillance or face detection or different other applications. So before we start talking about the different case study, we want to put some basic understanding of this distributed inference. We have to understand how this deep neural network is partitioned. So there is binary offloading, where this deep neural network is complex and it can run efficiently in one place, but it might be too large to run in the device, so it might be offloaded totally to the cloud. And now we have to capture the data at the end device and send that raw data all the way to the backend, similar to the traditional cloud-based architectures. Another way is to do this remote collaboration, where some parts of the neural network will be deployed and executed on the device itself, while other parts of the neural network can be executed in the back end. And in that case, the intermediate values of the distribution will be sent from the IoT device all the way to the back end. Also, we might have a situation where we have a hierarchical partitioning. Some of the neural network components will be running on the end device. Some of it will run on the edge. In this case, it's the tower. So communication of the intermediate results go there, but also some parts can run on the clouds, and intermediate results are sent all the way to the cloud, and the final outcome is generated at the cloud site. What we are proposing here and what we want to explore more is this localized collaboration, where we think that the decision has to happen fast. The decision needs to happen within the locality of the IoT or drone, these resource constrained devices. And we have the devices collaborating in a peer-to-peer way. So the part of the neural network runs on the source device, part of it runs on some other device, and maybe the result runs on a third device. So, and based on which type of architecture we go with, then the data transferred is different, whether it's the raw data or the intermediate values. The coordination needed is different, whether it's totally offloaded, things happen and you get back the outcome, or whether you are sending these intermediate values and getting back the outcome from your locality. And the assumption about the communication, computation, and available resources change drastically. We also want to understand that based on the models themselves, whether you are using a multi-layer perceptron with hidden layers, input and output, whether you're using a convolutional neural network, with some pooling, convolutional pooling, whether you are using residual neural network with these skipping connection to deal with the vanishing gradients, but also introduce a little bit of asymmetry, or whether you have just a randomly wired custom neural network, and in that case you have to deal with it as a graph and use different criteria to do the splitting. And based on the neural network and based on the dependency between the different layers and neurons, whether it's sequential dependency, so each layer is pointing to the next layer, and direct acyclic graph. And in that case, you can use the pair layer distribution, where each layer or two layers are assigned to a specific device, as we see here in A, or whether you have some parallelization, so you are breaking that layer into multiple segments or multiple feature maps, and now you can assign different devices to parts or segments of that layer and introduce parallelism within each layer. And in that case, you can use the pair segment distribution, or you have this general dependency, as we said, and then you have sort of a graph and a lot of dependency, and you need to use different, more complex techniques for distribution. And if we just look at the pair segment, you can see whether you are going to be splitting based on the input, so you will do spatial or filter splitting, or whether you will do it based on the output of the layer, and you will do something like channel splitting. So as IoT system experts, we have to have this knowledge of the architecture of the different neural network models, the different distribution strategies, and the implication on the outcomes, and then use the most appropriate distribution strategy. So now we will start the first case study, which is the privacy-aware distribution. In this case study, we will start with the objectives and the attack, the privacy threatening attack that we are looking at. Then we will look at how we built the optimization for this model. Then we will look at online solution, Heuristic, and then we will also look at the reinforcement learning solution, and finally look at the evaluation for both the heuristic and the reinforcement learning technique. So the objective here is to do optimal distribution of the machine learning deep neural network model. It's a CNN model among IoT devices, minimizing latency. There is resource limitation. The compute, the memory, the energy, all of these are limited. And in addition, we are adding this constraints of being privacy aware. So we are looking at a specific attack, an inversion or a reverse engineering attack, where we want to avoid that the intermediate IoT devices used for the inference, which are not trusted, will have access to the input data, which might be private. This work, part of it was published in Globecom, and part of it, the whole work is submitted to IEEE transaction of network science and engineering. So if we look more deeply at this specific surveillance, IoT surveillance application, you have a source device, a camera, that is generating those images, which we call requests. And these requests are moving, executing the inference. And as you see here, we decided to go with the pair segment approach. So device 1 is handling part of the middle layers, and device 2 is handling the other part of these middle layers. Device 3 is handling the fully connected layer, and device, the source device is handling the input and the output layers. And here we have this parallelization, as I told you, for the concurrent request. And the parallelization within one request across different devices. We want to avoid this reverse engineering attack, and we'll talk a little bit about this attack in the next slide. And we want to abide by the resource limitation. And our approach here is to design a distribution strategy that will allow us to preserve the privacy level as well as the resource limitation level. Previous work have done splitting of the model at a very late stage where it's very hard to decipher the data. This approach is maximizing the accuracy, but will require some specific resource in the original device that generated the data, because most of the neural network will be running on that device. So it will communicate less, but it will have a huge computational overhead. We can also extract the features of the data and send only the features, so that gives us some privacy, not very high privacy, because you can still deduce the data from the features, but it requires that you retrain, it requires that you do some processing at the end device, but it communicates less, and it has reasonable medium, I would say, computational overhead. We can add noise to the data to make it noisy data. This reduces the accuracy, similar to the feature extraction. It also requires to retrain on noisy data, and it has some compatibility issue with IoT and deep neural network. Require a lot of communication, because you will send the data with the noise, and you will also do some noise creation and mixing of the data, so it has some computation overhead. Cryptography was also proposed to give you high privacy, but it's also have huge computational overhead, and it will break some of your compatibility with IoT devices if it's not available there. Trusted execution layer, it assumes that everything is run on one device. It's running on the trusted computing base. It preserves the privacy, but also have a lot of computational overhead, and it does not communicate because it does everything on device. So it sacrifices the latency greatly. Our approach, we believe it has reasonable privacy because you cannot deduce the data. It's accurate, it does not require retraining. It's compatible with IoT devices because each device is handling very little work. It uses the pair segment, particularly the filter splitting approach. It has higher communication costs because you communicate with more devices, particularly to make the privacy higher, and it has lower computational overhead compared to other approaches. So if we look at the black box attack, the reverse engineering attack that we talked about, we are trying to avoid the case that the IoT devices being used for the inference are aware of the input data. And we have two insights when we experimentally tried this attack, and it's AI attack. So we train the model of reverse engineering different data by doing some learning of the data and doing some of this attack. So what we found out that if you go deep into the neural network, it becomes much harder to deduce the original image, the original data in this case. And if you split the model across multiple nodes, so each node will handle a smaller set of these segments or filters, then also it becomes much harder to do this attack. And the way we measure this is we are measuring the structural similarity index, SSIM. If you are in multimedia, you know this. It measures the similarity between the original image and the image or the data after you do a change on it. So we assume that if the SSIM is less than 0.4, then it becomes very hard to know what is the original data. And we see in this table, after we experimented with multiple data sets, that, for example, if you are looking at Khalifa, ReLU 11, if all of the 64 feature maps are in one device, you get a very high SSIM, 0.96, while if you move half of the feature maps into one device and the other half into another device, we go to 32, then you have 0.81. And if you reach 8 devices, and each device is now handling 8 feature maps, it goes to 0.27, and this meets our threshold and criteria of less than 0.4. So how did we take this insight and move it into an algorithm? We developed an algorithm here, an optimization that tries to minimize the latency. As I told you, the latency is our objective, by going through all the layers and all the requests, and for each layer and request, we calculate the transmission delay, which is the size of the data. The size of the data is O, and the rate of the transmission is P, plus the processing delay, TC. So we measure the maximum of the transmission delay and the processing delay, because we have all of these parallel branches. So we want the branch that takes the maximum amount of time, and we reduce this. And this optimization is really respecting all the constraints. We have the constraints of respecting the memory of each device, the constraint of respecting the computational resources of each device, the constraint of respecting the network bandwidth in each device, as well as constraint to respect the SSIM, the structure similarity matrix, as a threshold. So these are the constraints that we have for our optimal solution. This optimal solution is fantastic, but it has it's NP hard, so it takes a very long time to compute. Not very practical for our real deployment. So we devised 2 online solutions. The first online solution is a heuristic, where we respect the same constraints. We try to develop this, where the first, heuristically, we assign the first and last layer to the source device, and then we do the splitting based on the SSIM, respecting the threshold. And we also look at the delay and bandwidth. So we assign segment to these helper, these nodes that are waiting there to receive some execution load, based on these 2 thresholds of latency and bandwidth. So alpha is 0.7, beta is 0.3 without loss of generality. And we find out that if we respect the latency, if we balance the latency and bandwidth and respect the SSIM, we do the splitting and then reject if resources are exhausted in any node. And so we go iteratively and we do the allocation based on this heuristic. What we found out, and this is the results of the heuristic evaluation, we found out that we have 3 privacy levels. 0.4 is the highest privacy level. 0.6 means we accept SSIM up to 0.6. 0.8, we accept SSIM at 0.8. So when we have higher privacy level, we have higher latency, which makes sense. When we have higher privacy level, we have more rejects. So if we look at the 20 device case, 20 IoT device, and we look at the 0.4 privacy, the highest privacy level, we can see that we have 78% rejects. As we get more IoT devices, we are allowed to spread the load across more nodes, which means our latency is delayed because we are benefiting from the parallel execution, and the rejects are also reduced because now more resources are available to do the distribution. The other thing we look at is the shared data. We see that as we engage more devices, we are sharing more data. Also, we say that as we increase the privacy level to 0.4, we are sharing more data. And the main reason for that is that we are engaging more devices. So there is more communication happening to more devices. So that's why there is an increase in the shared data. The second approach that we are using is a reinforcement learning approach. And in that approach, the agent interacts with the environment. It specifies certain actions, and based on these actions, and these actions are assignment of workload to specific IoT devices, it gets rewarded, and the system state changes, and it interacts with the environment until it learns the best policy that maximizes the reward in the long run. Reinforcement learning is great because the environment here is complex. You have request load that changes. The problem space is huge. There is unforeseen environment and change in the conditions of the environment that requires some adaptation in real time. And those pervasive devices are volatile, dynamic, and joining and moving. So reinforcement learning, these learning episode, and in this learning episode, we do one layer in each episode, and each step of these episode handles one segment of this layer, and basically it assigns that segment to one of the devices that are participating in the inference. So at the end, I assign all the segment to different devices, and then I go for another episode. And every time I assign a segment to a device, I update the participant resources and the privacy level. If we look at this RL model also, we can see that the action is the assignment, the state is the CNN model, the layer, the segment, and then the memory resources M1 to MD, the bandwidth resources B1 to BD, and this compute resources C1 to CD, and the number of layers that is handled by each IoT device, and finally the action from the last iteration. And the reward function is basically trying to capture the constraints. So constraint one is making sure that we assign a segment to only one device. Constraint two is looking at the resources, making sure we don't exceed the resource threshold. And constraint three is making sure we respect the SSIM threshold. And the final reward function multiplies all of them and multiplies them also by an added part, which penalizes the algorithm if we choose too many devices or devices particularly with low resources. So we have to really pass all of the constraints in order to have a high reward. So all of the deep neural network models converge. We see that they learn, they do some exploration, and then they converge at different privacy levels. When the privacy level is higher, 0.6, the conversion takes a little bit longer. We also evaluated that if we have requests that are homogeneous, linet only, or CNN only, then, and these are simple neural network models, you have higher accuracy. If you have a complex neural network model like VGG, you have lower accuracy. If you have a heterogeneous workload, different requests from different neural networks, you also have relatively lower latency, around 70%. Also, we looked at the capacity of the IoT devices. In the left one, here we have 70% of weak devices, 30% of high-end IoT devices. In the middle, we see 50-50. In the last one, we have 0 limited or weak devices and 100% of the strong devices. And you see that the accuracy improves as we have stronger devices because they have more resources and they also have more resources to do the computation within one device. Here also we see the beauty of reinforcement learning. At episode 200, we change the environment condition. We reduce the number of available resources to half, and you see a dip in the reward there, but very quickly the model learns that there is limited resources now and goes and ramps up and learns the best policy to maximize the reward. And finally, this is the graph where we compare the heuristic with the neural network, with the reinforcement learning model. When you have Linet or CIFAR, which are relatively simple neural networks, the heuristic does better because the lesson there, if your model, if your environment is simple, deterministic, or can be done with a heuristic, so be it. But when we move into the more complex, heterogeneous request scenario from multiple neural networks, then the environment exhibits some randomness and exhibits some stochastic nature. And this is really when reinforcement learning does best, when this long-term reward maximization does better. So we find in this case that the reinforcement learning, this privacy is doing better, the dark blue line and the yellow line. And also, if you go to the point 4, you will see that the reinforcement learning is getting much less rejects, 0.28% versus 40% in the heuristic. So heuristic has its place. The reinforcement learning is better when you have a stochastic nature. The extension of this work is really where we are moving into using multi-agent reinforcement learning, where we have multiple surveillance systems in this case. Each system is using the same IoT devices substrate, but they are also trying to compete. They are basically competing for the resources of these IoT devices while collaborating on the privacy objectives. So this is the agent system. Agents are competing for resources, but they also want to maintain the global privacy of the data. So they are sharing some of the states. And we are experimenting here with different multi-agent architecture and trying to see which is the best approach and how does the heterogeneous scenario and the homogeneous scenario affect the reward function. And last but not least, and I will try to go quickly over this work, is the mobility-aware distribution. And in this case, our goal is similarly to optimize the distribution of the machine learning model in mobile drone swarm while still minimizing the latency, to minimize the latency as my target. There's a lot of resource constraints. Probably energy is the biggest one, but also computation and memory. And there's also very dynamic network condition because as we move far or close to each other, the network is affected and the rate of sending gets affected. This work was published in IEEE IoT journal. And as we see here, we have multiple drones. And in this case, we decided to go with the pair layer approach. And let's reflect. In the previous work, we did the pair segment approach. And the main reason for that was that we have that privacy objectives that require us to split the model into smaller things, and we generally have a large number of these IoT devices that we can engage. So each IoT device can handle relatively small computation, while in this case we are going for the per layer because each UAV can handle a full layer comfortably, and we have few of these UAVs, so the per layer approach makes more sense. So if you go for VGG 19, you need maximum 19 UAVs, probably less because you can put multiple layers in one UAV. And in this case, as before, it's a surveillance application, so an image is captured by one UAV, and that's a request. And that then request is sent to other UAVs based on what layer is running where to get the final outcome. Similarly, it's an optimization. We are trying to minimize the latency. And here we are going for the per layer approach. So we are similarly minimizing the latency of the transmission. K is the size of the data, P is the sending rate, and TS is the sending of from the source. We add the sending from the source, and in this case we also have a negligible processing delay, so we don't capture it. If you look at the rate, P is a function of the distance between the two UAVs. The PIK here is a function of the distance between the two UAVs. And we have the same type of constraints of resources, memory, computation, executing each segment in one device, and also making sure that we also have this binary decision variable of whether this device is running this segment of that layer. The mobility model here, we looked at the two mobility models. The homogeneous mobility model, where all the nodes within a swarm are relatively at the same distance from each other as we move. So they move at one pace and they keep the distance. Or we have this non-homogeneous mobility model, like the group mobility model, where the swarm is still in close contact, but the distance relatively changes as they move along, but they keep the structure of the swarm. So the homogeneous swarm formation is, you look at example 1, 2, and 4, and the non-homogeneous, in this case, the reference group mobility model is this model in 3, as you see. They keep the formation, but relatively they change distance from each other. We developed that optimization, and now we are testing it with Linux. And here we want to show you the effect of having more nodes. N is the number of nodes. M is the size of memory. So we are showing you the memory resource effect. And here we can see clearly that when we have more memory, when we have 512 megabytes of memory in the green and the yellow case, we are able to process generally more requests. And when we have less memory in the blue and the orange line, we are able to process less requests. We are also getting higher latency when we have lower memory. We are getting lower latency when we have more memory. The second effect is when we have n equal 10 nodes, if we have 10 nodes available, or if we have 15 nodes available. When we have 10 nodes available, in the case of the blue line and the green line, more when we have the same amount of memory, 512 in the green and the yellow line, when we have more available resources through more drones, 15 drones, then we are able to process 25 requests. When we have 10 drones, we are able to process 18 requests almost. Same when we have 255 megabytes. When we have more drones, in the orange case, we are able to process more requests than the blue case. Same here with the shared data. We are sharing more data when we have less memory. So when we have less memory in the blue and the orange case, that means that the resources for each UAV is more limited, so we need to engage more UAVs, which means sharing more data. When we have bigger memory, we are able to share less. We also tested the communication versus computation latency. When we have 10 UAVs and 15 UAVs, and we can see that computation is the biggest factor, as we have low number of requests, but as we get more number of requests, the communication becomes a bigger segment, especially in this 15 case. When we reach 10 requests, then the communication becomes very expensive, because we are engaging UAVs that are maybe far away or have very limited resources. So we see that communication becomes more important with more requests, and with more UAVs, we have more leverage and we can process more requests with 15 than with 10 UAVs. We compared our optimization with 3 heuristics, and we can see very clearly that we have the best latency as we grow the number of incoming requests. The closest one, the closest heuristic to us is the one which chooses the nearest UAV to offload to. And the reason for that is that if you have a near UAV, then you have a higher rate of sending and you can optimize in a better way. When we look at the mobility case, now we have the reference group mobility model. We have our algorithm optimization with mobility prediction. So we predict the path of the UAV up to 10 steps in the future. So we compare ourselves against the state-of-the-art approach, which does the distribution. What we find out is that the state-of-the-art approach, as we go more steps into the decision-making, it diverges more, because as you go more, the UAVs move away and far from each other, which affects the distribution. But for our approach, since we do this mobility prediction, the added mobility prediction into our algorithm, we find that we are able to maintain consistent latency up to the 10 steps. We are also doing old with the mobility prediction and old without the mobility prediction, and you will find that with the mobility prediction, we are getting lower latency overall. So in general, we explored this problem in 2 case studies here, but really our exploration is very limited. We did not consider loss and link failures that can affect us, so we can look at more rich communication models that look at failures and their effects. We also did not look at the physical layer properties. We kept the networking model as a sort of a function of the distance, but there's a lot to be optimized based on the physical layer properties and understanding what can happen underneath. There's also opportunities to look at locality awareness. There are 2 types of data here: the model itself as data, and the actual data that comes from these requests can also be thought of as a thing that we can optimize for. If the data is very high granular data, maybe the same data was already sent to a node before, so we can allow that node to recalculate or use the previous outcomes, or the model was sent, or the model now does not fit into all the nodes, so we can bring it on demand. There's also the idea of mixing between the inference as well as some of the mission that are done by these applications. So for the UAV, if we are looking at path planning in addition to inference, how can we respect this resource constraint as well as navigate through a certain path that maximizes some reward? Also looking at different applications, as we saw earlier, the nano robots with the very limited resources. Maybe then we can look at putting one neuron in one of these nano robots and then doing some communication. So the trade-off between communication and computation and the resource limitation in terms of energy. Finally, looking at the per layer and per segment, we do a little bit of a judgment of what works here and what works there, but really we did not explore the full design space, especially the per segment with the different input and output splitting. We can do a lot more experimental approach, vary the different parameters, and get different insight about what works and what doesn't. So in conclusion, the pervasive edge computing can potentially enhance scalability and security of IoT-based application. Mobility prediction is essential for the distributed inference in this multi-drone, and we are planning to look at different approaches, maybe using reinforcement learning to do this prediction of the path. We also think the layered approach worked very well for this multi-drone case because of the reasons we mentioned, the density and the network dynamics. Segment-based worked very well for enhancing data privacy while maintaining lower latency. Finally, using reinforcement learning in a centralized or multi-agent approach will be nice to either do the resource allocation or do the path prediction of the drone. And I would like to give credit to my teammates from Hamad bin Khalifa University and College of Engineering at Qatar University. So this is a collaborative work. A lot of people were involved in these studies, as you saw. This also was funded by the Qatar National Research Fund, MPRP13S grant, which was funded in the last cycle. And if you still have any questions, I'll be more than happy to talk to you.
Yes, thank you very much. Really a very interesting topics actually. Okay, so many topics discussed, and the presentation was really nice and let's say educative. So, well, questions from audience. If you have any question, you can please directly unmute your mic and ask the presenter.
Can I ask a question, even though I was involved with the work? This is
Yes, go ahead. Yes, Dr. Mohsen, go ahead.
Thank you, Dr. Aiman. Very nice presentation. As I would like to add to the comments of Dr. Nizar, very, very interesting future directions that you've elaborated on. In terms of I'm really interested in the nano robotics or nano robots that you've alluded to. What I mean, there is a lot of talk about it. I know you haven't done any work, but what do you think the future of this, especially in the medical field? I saw a video recently that that these robots will help in will help in opening veins, blood veins, you know, in the human, and that will help for medications, and will help
Yes.
localize certain tumors, and try to automatically. So, what's your opinion about what type of work that we can do with our students to be able to achieve such predictive measures?
To be honest, this is becoming a very interesting and hot areas, as we are able now to put these very tiny robots, and as you said, they can open blood streams. They can be used for cancer, particularly drug delivery, delivering the drug to very targeted places, which it was very hard in the past because they had to go invasively and cut and do some damages to some of the tissue. They can also use it for nano sensing. There's some diseases and some phenomena in the human body which have very small particles in a very low concentration. So they can use these nano robots for that. And our goal there is to look at these nano robots as a platform similar to our IoT devices and UAVs, even though it's very tiny, but then maybe few neurons can be run on one of these, and maybe that robot can have some communication and some energy capabilities. So within the time it's doing the mission, multiple of these robots can use maybe the communication and the computation resources to run some smart algorithms to collaborate on how to tackle the disease and how to maybe capture some of the phenomena happening in our body. And it will be very challenging because the distribution available, the architecture of the neural networks, the expected computation versus communication trade-offs are going to be very interesting to think about. So I
Thank
think
you.
this area is
Thank you.
very
That's very
rich.
important. Thank you very much. I think it's a very niche area, and I think we should get into it, you know, in the near future. Thank you very
I
much.
totally agree. Thank you. Thank you.
Thank you, Professor Mohsen. So we have one question from audience that say, so they are thinking about your opinion, Dr. Aiman, about how this work will extend to wearable devices, okay, and healthcare. So what do you think that can be the impact, okay, on wearable devices?
I think wearables are an ideal native component of this IoT subset, because if you think about most people now, you will see that they have a mobile phone, they have a wearable, whether it's a watch or something else. They have maybe some other sensors surrounding them. So if you think at any point of time, you can think that these wearables are doing two tasks. First of all, they are capturing some of your vital signs, they are capturing some of the data about your health and well-being. And they can also be a platform where you execute some of these initial algorithms. So the wearable will actually do some pre-processing of the data, filter, extract features, do the initial part of the neural network, and maybe some other device like your mobile phone or some sensor surrounding you can do the other part. So I think wearables are very critical in this fabric. And they also exhibit real constraints in terms of the energy requirement and the communication capabilities that they exhibit.
Yeah, I totally agree. I think that it is the place.
you.
Okay, so wearables will be the place. Okay, so one more question, Dr. Ayman. So, I really liked whenever you compared, okay, or you took into consideration communication versus computing and the optimization. Well, it is really interesting to find some trade. Well, the trade-off is there, but to find the optimal point. Okay, but my question is, have you dealt with the energy consumption of the IoT devices? Because some IoT devices usually are, well, they are small size, small battery. So to run such kind of algorithms on them, most probably will be heavy in terms of power consumption. So what do you think about the power consumption and trade-off with all the algorithms whenever especially are distributed?
So to be honest, when we started this work, we started a lot with the direction of latency was sort of our main thinking was how do we minimize latency. But toward the end, when we started to get some result and we were able to minimize the latency, our biggest concern, which turned out to be probably a little bit more important or at least equally important, is the energy. Because as a UAV, you have a lifetime of maybe 30 minutes maximum in the sky before you have to go down. As an IoT device, you have a lifetime maybe of a day if you are doing operation at a very low frequency. But if you are doing what we are talking about here, which is processing data real time, continuous requests, deep neural network, that will really shrink down the lifetime. So what we are thinking now is really to shift our optimization to be more focused on the energy, minimizing the energy, and taking the other things which are latency and the resource constraints and the other things that we have looked at as constraints. And that will really, especially for the UAV case, that would be the direction that we should follow. I expect it will expose that some of these systems are very fragile. So if you put a lot of computation and significant communication, communication being more expensive energy-wise than computation, I will think that you might be reverting your priorities to do more things in one device, slow yourself down a little bit rather than communicating more. So I would say it's very interesting. It will conflict some of the other constraints, and that will be interesting to see.
Yeah, more trade-offs to consider.
Very complex ones.
Yeah, it will be really well. It is well. It is. This is the way to know how it will work. So one last comment from audience is that if you can share your publication, I think all of them are shared on IEEE Explorer and
Yes.
on archive, right? Yeah.
Yes, all of them are in archive, and some of them were already published, so you will be able to find them in IEEE Explore.
Okay. Well, if there is anything that they don't find, can they contact you to?
Sure.
Yeah.
The only one that is not published probably is the privacy one, the full version and the
Okay.
journal version. We'll be happy to share and discuss.
Okay. So, and with no more questions from audience, then it's time to thank you again, Dr. Ayman, for this very interesting presentation and topics, okay, discussed. And we will be posting the recording on our CSIM YouTube channel and sharing it with all the community. So if anyone has more questions, they can approach you by email.
Thank you. I'll be more than happy to.
Thank
Thank you for your invitation, Professor Nizar. Thank you.
It was a pleasure to have you here, and thank you for all the attendees and participants. And we look forward seeing you in the future CSIM seminars. Thank you all, and bye-bye.